Alright, ladies and gentlemen, welcome back. I know after watching the last video, you have been chomping at the bit to get at this, the binomial distribution. And you're probably going, well, we already studied binomial expansions. Is that related to this in any way? And you bet you're right it does. It's the same thing. But we're talking about it with the lens of probability on. So if something is going to be a binomial distribution, it has to satisfy the probability distribution criteria, but there's a little bit more to it. There has to be a fixed number of trials, so we have to be performing this experiment 5 times. The trials must be independent of each other. It means that what happens on the first trial can't affect what's on the second trial. So something like sampling without replacement would not fall under the umbrella of a binomial distribution. There must be 2 outcomes. Oh, binomial, that's right, 2 things. Binomial distributions have 2 possible outcomes, and we generally classify them as either a success or a failure. And we generally use P to represent the probability of success and Q to represent the probability of failure, and those are complements of each other. And finally, the probability of a success must remain constant from one trial to the next. And what we have is the notation X is distributed as, random variable X has a distribution of a binomial with the parameters N and P. N is the number of trials. P is the probability of success. So the probability that X equals R, so the probability that we have R successes, the random variable X is the number of successes in one of these. It's given by N choose R, this is that combinations operator, times P to the R, Q to the N minus R. For instance, if X is distributed as a binomial with 3, 1/2. So 3 trials, probability of success is 1/2. I want the probability that X equals 2. Well, we might do, I'll change this to 1/3. 1/3 times 1/3 times 2/3. That's 2 successes and 1 failure. And you might say, well, we're done. That's the probability of getting 2 successes. But remember, they don't have to go in the order success, success, failure. There's actually choose 2 ways for this to happen. This goes back to our probability study. And this is 3 choose 2 times 1/3 squared times 2/3 to the first. Probability of success is 1/3. There are 2 of them. Probability of failure, Q, is 2/3. And there's only 1 of those. And the combinations operator counts the number of ways that we can get this possible outcome for the random variable. And let's do some examples. X is the number of 6s when you roll a die 7 times. Is this a binomial? Well, let's think about this. Is there a fixed number of trials? Yes, we're doing this 7 times. Are there 2 possible outcomes? Yeah. It's either going to be a 6 or it's not going to be a 6. We don't care what else it is. It's either we care if it's a 6 or not a 6. Is one roll independent of the other? Yeah. And finally, does the probability change from one roll to the next? No. The probability of rolling a 6 is 1/6 every single time. This is what we would call a fair die. And it doesn't change, we don't change the die after one roll to the next. So what's the probability that X equals 3? That is, what's the probability that we get 3 6s out of 7 rolls? It's important to interpret what this probability notation means. So, using our binomial formula, which is identical to the binomial expansion formula that shows up in your formula booklet for IB, we're going to do 7, choose 3, times probability of success. Okay, what's P? What's little p? It's 1/6. That's the probability of success. Probability of failure is 1 minus p. Probability of failure, probability of getting something other than a 6 would be 5/6. So we're going to do 1/6 to the third. We want 3. We're looking for the probability that we get 3 successes times 5/6 to the, well, how many, if there are 3 successes, how many failures will we have? There will be 4. And this is just purely number crunching at this point. And what we get is approximately 0.0781 to 3 significant digits. Now, guess what, guys? We can do these sorts of things in our graphing calculator. What we're going to do, go into Menu, Probability, Distributions, and we're going to go down and we're going to find, binomial probability density function. Number of trials. Well, this problem said we had 7. The probability of success, P, was 1/6. If I don't put in an X value and just press OK, look what it gives me. It gives me the probability of 0, 1, 2, 3. It gives me the entire probability distribution. But if I go back in there, do 7, 1/6, and type 3, we press OK. Now notice there's an extra number there. There is our probability of getting exactly 3 successes out of 7, and it's exactly what we found calculating by hand. Sweet. Second example with this, what's the probability that X is less than or equal to 3? Well, this is a cumulative density function, and what it means is what's the probability that X equals 0 plus the probability that X equals 1 plus the probability that X equals 2 plus the probability that X equals 3. And we could calculate all these by hand and add them up if we want, but we have our calculator. And you might be thinking, that's great, we've got this whole list of things right here. We can just add up the 0.279 plus the 0.301 plus the 0.234, and you're right, we could, but there's a better way. You might have noticed that in this distributions menu, there's binomial CDF. Number of trials. Well, the number of trials was 7. Probability of success is 1/6. Lower bound, I want to add up everything from 0 up to and including 3. If it said what's the probability that X is greater or equal than 3, the lower bound would 3 and the upper bound would be 7. And we type this in, we press enter, and voila, the probability that X is less than or equal to 3 is 0.982. It's that quick, that simple. For a cumulative density function like this, you're probably not going to be doing a lot of it by hand. At least if you did, the numbers would probably be working out fairly nice in your favor. The parameters of a binomial PDF is the same as any probability distribution. We have mean, median, mode, standard deviation or variance, but they're calculated slightly differently. If X is distributed as a binomial, then the expected value or mean is simply the number of trials times the probability of a success. And the variance, the standard deviation squared, is the number of trials times the probability of success times the probability of failure. The calculation for this is much more simple. So, we're going to do an example using our GDC. And random variable X is distributed as a binomial with the number of trials 4, and the probability of success being 0.25. We want to find the mode and we want to find the median. In our graphing calculator, we're going to open a list and spreadsheet page, and I'm going to call this column, I don't know, I need to name this variable. I'm going to call it R, doesn't really matter. And we're going to list the possible values that our random variable can take, 0 through 4. And then in column B, we're going to put equals. In the second row, we're going to type in a formula. And we're going to go into menu, and under statistics, we'll grab the distributions menu. We're going to scroll down to binomial PDF, and we're going to put in number of trials. Okay, the number of trials is 4, and the probability of success, P, was 0.25, and the X value, I'm going to put X in, or I'm going to put my variable in, R. And I hit OK, and it puts my formula in, and it says, is it a column reference or a variable? That's a variable that I defined. And I press enter, and here's my probability distribution for this binomial probability. To find the mode and the median, what do we need to look at? Well, the mode is the most probable outcome. Well, we can see that from here. We know that the mode is x equals 1 because it has the highest probability of happening, 0.422. To find the median, however, we need to know the cumulative frequency distribution. I'm going to do a new formula in column C. Press equals under statistics, distributions. We're going to grab the binomial CDF, and this time we do 4, probability of success 0.25 again, and that's all I'm going to put in. It's going to ask me to put something in there, but you know what? I'm not going to. I'm going to delete out the 0 to 4, and I'm going to press enter, and it populates that column now. Notice my n probability is 1. We now need the median, so what are we looking for? Well, we're looking for the two data values, one that's this biggest data value less than 0.5, and the second, the smallest data value that's greater than 0.5, so the biggest less than 0.5 is 0, smallest greater than 0.5 is 1. We add them together and divide by 2. Our median is 0.5. So there we go. Calculator can be very handy for these distributions. And finally, we have a biased coin, so it is twice as likely to show tails as heads. The coin is tossed 5 times and the number of tails is noted. Find the expected value and find the variance for this magical weighted coin. Well, this is a binomial distribution. X is distributed as a binomial. How many trials are there? There's 5. And what's the probability of a success? Well, what are we measuring? We're measuring the number of tails. What's the probability of getting tails? It's twice as likely to show tails as heads, so that means we could think of it as being tails, tails, heads. It's twice as likely to show this. It's not 1/2. So the probability of success is going to be 2 out of 3. So what is our expected value? What's our mean? Well, it's NP. 5 times 2/3, or 10/3. What's our variance? Well, it's NPQ. 5 times 2/3 times 1/3. So our variance is 10/9. And finding mean and variance is really that simple for a binomial distribution. And that, ladies and gentlemen, is that.